Okay, good afternoon, everyone, and welcome to this afternoon's session on system dynamics. Partly sad, this is the final session in this phase that you'll have with me, and your training. You'll have a few more sessions with Tom and Sean coming up, and also with Luca tomorrow, our guest lecturer, who's got some great thing on building an ED model in R, which I'm looking forward to. Not the R bit maybe, but certainly the building the ED model bit. But this will be the final session you'll have with me until phase 2, when I will at some point write these 3 remaining sessions. And once I've taken a suitable break over Christmas, I will look to do that. But just a few things really to say. So first of all, I would urge you all to reflect back on your HSMA training journeys since October, not too long ago, when we were teaching you the very basic principles of modeling and data science, and how to code. And in fact, it wasn't so long ago we were showing you how to put the words "Hello World" onto the screen. And since then, you've had quite a learning curve, and you are now using those new Python skills to build neural networks, to generate maps, to build complex agent-based simulations, to build models of queues within a system, and all this fantastic stuff. So really well done to all of you, because I think you've come on so far since starting this course, and we are aware this is a very intense course, and we advertise it as being intense for a reason, because there's a lot of stuff that we chuck at you on this, because we're basically, as we said at the very start, we're kind of showing you pretty much a sample of everything we do. So there's lots to it, but hopefully you're starting to find now certain areas that you're particularly interested in, and that you'd like to dive deeper on for your projects. And that brings you on to the second reminder. Next Monday is the deadline for submitting your project pitch videos, that your 2-minute videos. Do make sure you do that. You have basically until the end of Monday, so until 1 minute to midnight on Monday. So do make sure you read the instructions that I posted about that a little while back, to make sure you're happy with that. But as I said before, the key advice is give us an indication of why this thing you want to do is important, how you want to do it, an indication of the kind of data you've got to support it, why we should care about it, because ultimately the key thing we're looking for are manageable, practical, but impactful projects. So you're much better off going with stuff that is small but important. Sometimes you want to look at something a bit more exploratory, and that's okay, because it might be a really important area too. But always think about what's the impact, what's the potential impact if we can do this work, and that's what it all boils down to ultimately. And that's our if we were prioritizing the criteria, that's absolutely the number one, and quite upfront about that, the number one selection, the way in which we'd select your projects. So make sure you get those in, and obviously don't forget about the Python assessment next Wednesday. That's now been finalized. I promise you I've made it hopefully as straightforward as possible. It's not there to trick you. And I hope that most of you will be quite surprised by it's fairly straightforward. As I said to you before, you will need to do have the sort of basics of object-oriented, how to write classes and stuff like that. But and then the other stuff that we covered in those first 3 Python sessions. I'll tell you now as well, we won't be doing anything on file reading and writing, for the simple reason, you should absolutely make sure you're comfortable with that, but for the simple reason that it will be an absolute nightmare to try and deal with file systems in an assessment. So we won't be doing that. I've also tried to make it as fun as possible, as much as you can make an assessment fun, but I've tried to make it as friendly and fun as possible. So it's got a rather fun theme, which I'm hoping at least some of you will will enjoy, and those of you who don't, at least you've lost nothing. So that's all coming up. If you do have any questions about the assessment, do let me know. Obviously, I can't tell you what's in it, other than the advice I've already given you. But it is an open book assessment, so you can look at your slides, refer back to your slides, but do make sure that you're working alone. Don't sort of copy off each other. We have unfortunately had incidents of that in the past, and I don't want anybody to feel as though that's what they have to do, because it's not designed to be that. It's, as I said, we'll only be looking at your assessments. I literally will be casting my eye over them. If you put in your project pitch, we think this is a good project pitch, I will just look over what you've written to make sure that you've kind of grasped enough of Python that I can see what you're trying to do, and that looks okay. What we're basically looking out for is to make sure that somebody just has no clue in how to code in Python, and you wouldn't be able to do the project that you're saying that you would. So that's all we're trying to do. It's not a case of seeing who's better than others. That's not how we work this. Oh yes, sorry, got a raised hand, Janine.
Yeah, just with the assessment, we were going to submit a proposal with a lead and kind of to support people. So do all three of us need to do the assessment, or is it just really relevant for the person who's the lead?
Yeah, so it would only be the lead that would need to do that, and that's the only requirement we would have. You may want to, if the others want to sort of take the assessment for their own purposes, I will share the solution after, they're more than welcome to do that, just to see what they're comfortable with. But certainly in terms of requirements, we only need one person, the nominated project manager for that project, to be the only person that needs to take that. So yeah, no, that's fine. Any other questions, sorry, about the assessment, actually, while I'm talking about that? No, okay. As there'll be a Zoom call next Wednesday. Join that Zoom call. I will give you basically an introduction to what you're going to be doing. I'll be able to take any questions before I give you the assessment itself. And then you'll be set the assessment, and you'll basically, I'll explain how that will work. All you will need in terms of software is the IDE of choice. I'd recommend you use Spider for this, but if you want to, you can. Basically, what you'll need to send me on Slack is a .py file. So you use whatever IDE you like using, as long as you can generate a .py file from it. For most of you, that'll be Spider, but I know if you use other IDEs, that's absolutely fine. Okay, so as I say, the key thing I wanted to say about that is try not to worry, and hopefully it'll seem a bit like light relief after what you've been doing over the last few weeks, which has been far more intense than the stuff that you'll be tested on, which will only go as far as the stuff that we covered in those first 3 Python sessions. So there'll be nothing more complex than that. We're not going to ask you to build a neural network or do anything with generator functions that we covered in SymPy, nothing like that. So it will just be basic Python stuff, but there will be an emphasis on object-oriented code. Okay, let's plow on with today. So system dynamics. So in the last, this is part of the kind of modeling whole systems module. And in most of this module, Sean will be taking you through network analysis, which you obviously already had an introduction to in the first session of the module. And I think this week's doing network analysis again on Thursday. So he'll be taking through how to actually do this stuff in Python. And network analysis is a fantastic approach for modeling whole systems, and probably the preferred approach for a lot of what you will be doing. But there is this approach called system dynamics that we do like to touch on as well. And system dynamics is one of those, it causes a lot of divisiveness within the team. It's not got many fans within the team. And part of the reason for that is that there are a lot of bad system dynamics models out there. But there are enough good system dynamics models when people really get to grips with this thing that I do believe it is still worth teaching you this. But there is, I need to put in this warning that there's a temptation, particularly as I'm sure you'll be delighted to hear, this is the one method we show you where there's no code. You don't code anything. It's all drag and drop. You don't need to program. So it's very tempting to try and see everything as a system dynamics problem. because you can drag and drop and it's a bit easier to put models together. But be careful, and there is a danger you kind of fall into the trap of trying to make a system dynamics model do something else. And you can, any modeling approach you can fudge to do something else pretty much. But it tends to happen with system dynamics quite a lot. So the system dynamics has a particular purpose, which I'll talk about this afternoon, and you need to think very carefully about whether it's the most appropriate approach for you. But there are certainly elements of system dynamics as an approach that may be able to help you regardless of what you're doing, and I think that's why it's certainly worth looking at. I mean, we've got a couple of people who've got system dynamics expertise, including one of our training mentors on this course, who are probably far better than I at system dynamics and will be able to, and certainly a lot more experienced. And so if there are any system dynamics projects, I'm sure they will be able to support you on that as well. I'll also link you after the session as well to the recording we did from last year's system dynamics session, which was a little bit different. But one of the things we had in that was one of our HSMA alumni from HSMA 2, who actually put together a fantastic system dynamics model of when the COVID pandemic started, of the sort of bed usage, and working out how they were going to needed to sort of align their bed requirements across the county to what was happening in terms of the progression of the virus. It's really, really nice thing. So there's a presentation of that in that video that's certainly worth checking out. But let's talk about system dynamics, because it's been around a long time and it's quite an interesting approach. So when we talked about discrete event simulation, we talked about how essentially it's for modeling queuing problems. So we see everything as a series of processes, and those processes require resources, and you have entities that are queuing up for those processes and those resources. Then when we talked about agent-based simulation, we talked about how this is kind of individual based modeling, essentially, that you're focusing on the individual and what all the individuals in your system are doing and the way they behave and the way they interact, and how that then causes this kind of population system level emergent dynamics. System dynamics is kind of the goes to the other end of the spectrum, away from agent-based simulation, and it's kind of focusing very often on sort of high-level dynamics, and it's basically an approach in which the structure of the system itself is the thing that you're interested in. So the particular components, the way in which the components within a system relate to each other, that's what you're capturing, that's what you're modeling. And so the fundamental principle of system dynamics is that structure determines behavior. Okay, so it's all about the dynamics of the system. The clue's kind of in the title, but that's what it's about. It's where you get really good system dynamics models is where they're trying to understand and unpick what the way in which a certain system is configured or has emerged, how that's leading to something happening. And that's usually the kind of question you might explore with a system dynamics model. So we're going to start off this afternoon by talking about qualitative system dynamics, and then we're going to move on to quantitative system dynamics. So we're going to start with qualitative, which basically just means no numbers. Okay, but this is quite a useful approach. Some of you may be familiar with some aspects of this because they're known in their other guys as causal loop diagrams, but they are essentially a form of qualitative system dynamics, and they can be quite useful to try and unpick problems and systems and complex systems. So basically, with qualitative system dynamics or causal loop diagrams, what you're trying to do is you create a map of influences and their directionality, and I'll come back to that in a moment. And the thing that you're particularly interested in is looking for things called feedback loops within the map. And again, I'll come back to that, but it's the feedback loops that you're particularly interested in because they indicate where you might have particular kind of behaviors that are emerging as a result of the way in which the system is set up. So what you're trying to do with this map is you're trying to generate it so you can draw some insight from it, and from the feedback loops that you identify, to try and better understand why certain system behaviors are emerging, and of course, as with all modeling, what you might be able to do about it. That's ultimately why you're building these models. So let's think about some influences as examples, first of all. So we might, for example, have an influence that says the number of people who are accessing GP services will influence the waiting time to see a GP. And in system dynamics, we can, and causal loop diagrams, we can indicate what's known as the polarity of the influence. And we indicate that with either a plus or a minus. And a plus basically means both things are moving in the same direction, whereas a minus means they're moving in opposite directions. And it's quite, this is a common confusion that people often think of. In some ways, it's quite a bad way to label it, because you often think of plus meaning it goes up. It doesn't necessarily mean that. It might just mean both things are going down. So a plus means they're going in the same direction, and a minus in opposite directions. So here's an example where they're going in the same direction. This is saying, as the number of people who are accessing GP services increases, the waiting time to see a GP will also increase. They're both going in the same direction. Similarly, vice versa, if the number of people who are accessing GP services decreases, the waiting time to see a GP, you would expect to decrease as well. So this is influencing that, and they're both moving in the same direction. Okay. Here's an example of a negative polarity where they're both moving in opposite directions. So we've got the number of people admitted to hospital, which is influencing the number of beds available in the hospital. So they're going in opposite directions here, because as the number of people who are admitted to hospital goes up, then the number of beds available in the hospital reduces. So as that goes up, that goes down. So they're moving in opposite directions. So indicate that with a minus. So when you're building up your causal loop diagram, you're building up these maps of influences, the way in which certain factors influence each other, and indicating their polarity. But these are the things that you're looking out for, these loops where things loop back around on themselves. Okay, and you get two different kinds of loops. And here's an example of the first kind of loop, which is known as a reinforcing loop, or in colloquial terms, you may refer to them as vicious circles, or maybe even virtuous circles. It might be something that's a very positive thing, but unfortunately, it's usually, when you're exploring it in this kind of stuff, it's usually that it's a negative thing that you're seeing. So here's an example of a reinforcing loop. So we've got the number of people who are accessing GP services. Okay, that influences the waiting time to see a GP, and they both go in the same direction. You've got more people accessing services, means more waiting time, a longer waiting time to see a GP. This in turn, the waiting time to see a GP, will influence the number of sick people in the community. And again, they're both going in the same direction. So as that goes up, as the waiting time increases, you're getting more sick people in the community. Here's where the loop closes, because then we can say, well, the number of sick people in the community, as that increases, so does the number of people accessing GP services. And so you've got then a closed loop where you've got this kind of snowballing effect, which, you know, we're all familiar with this kind of effect here, that you've got growing demand, that's putting more pressure on the system, which is, it's causing essentially more demand, and you're getting this kind of snowballing effect here. And this is known as a reinforcing loop in causal loop diagrams or system dynamics. Now, this is obviously pretty simple to identify that this is a reinforcing loop, but there's a way in which you can do it, particularly for more complex loops. And the way in which you identify whether it's a reinforcing loop is, a reinforcing loop will have either 0 or an even number of minus signs. Okay, this means that the same conclusion is reached each time you loop. So if I say this through, as people accessing GP services, as that increases, waiting time to see a GP increases, number of sick people increases, accessing GP increases. So I've ended by saying the same thing I did when I started. You're probably thinking, what on earth is he talking about? It'll make sense in a moment. But this is, you count up basically your plus signs, and if you've got count up your negative minus signs. If you've either got none of them in your loop, or you've got an even number, then you kind of get a double negative effect and they cancel out. Then you have a reinforcing loop. Okay. Let me, in fact, before I go on to look at the other type of loop, you might say, well, why would we care about this? And of course, the important thing is not just often not just when you've got this self-contained loop here, but of course these self-contained loops often spill out into other things. And so, as we might imagine, this kind of loop here, where you've got an increasing number of sick people in the community, can increase the number of people who are attending ED. And so you've kind of got a snowballing reinforcing effect here that's constantly increasing this, which is then placing demand, increasing demand over here. And so you've kind of got this leak from your loop that's causing this effect. And so by identifying that there's a loop here, and identifying you've got a problem here, one approach, if you saw this in your model, you might say, well, can we do something about trying to break this reinforcing loop, such that, because if we do that, it'll help solve the problem over here. Okay, so those are reinforcing loops. The other kind are balancing loops. Balancing loops are basically where things balance themselves out. Okay, so you don't get a kind of net positive or negative effect, they just balance out and they're kind of negated. And balancing loops, typically when you find balancing loops, it kind of indicates something that you don't need to worry about, because actually it counters itself out. And so that in itself can be quite useful. So let's consider a balancing loop. So let's imagine we've got the number of people admitted to hospital. As that increases, the number of beds available in hospital will decrease. Okay, so we've got a negative polarity there. As the number of beds available in the hospital decreases, the capacity to admit patients also decreases. We've got a plus sign, they're both going in the same direction. Okay, so beds available decreases, capacity to admit patients decreases. As capacity decreases, the number of people admitted to the hospital decreases. Okay, so it balances itself out because they're going in the same direction, which, if you think about it, makes sense. It must do, because otherwise you don't, sort of see people spilling out of hospitals and more and more people just, sort of climbing on the roof and, well, maybe to some extent, but things balance out. If the hospital's full, there's only so much it can expand, and then you just can't take any more people. And so you kind of get a balancing effect where it's balancing out the number of people who are admitted to that hospital. Now, the way in which you identify a balancing loop is you count up your minus signs. If you've got an odd number of them, remember, if you've got an even number or zero, then it's a reinforcing loop. But if you've got an odd number of minus signs, then you've got a balancing loop, and that's because you'll end up with a contradiction when you loop round. So again, I'll say this, and hopefully now it'll make sense. So let me say this out loud. Number of people admitted to hospital. If that increases, that decreases number of beds. That decreases capacity to admit patients. That decreases number of people admitted to hospital. And I started off by saying, as that increases. So I've reached an opposite conclusion. Okay, so as I've talked that through, I started off by saying increases, but when I came back around the loop, I was saying decreases. So that indicates that a minus sign has essentially negated that. And if you think about it, if you've got an even number, as I said, they'll cancel them out. It's a bit like a double negative. But if you've got an odd number, it'll end up kind of reversing the polarity of that loop. So that's what a balancing loop is. Okay, so the easiest way to identify is to basically count up your minus signs within your loops. Okay, so let's get really complex now. Let's consider a system. Let's think about chickens and eggs. Why not? Okay, make sure you follow this. Chickens lay eggs. I think we can all agree on that. Eggs hatch into chickens. Okay, hope you're with me so far. More chickens means more eggs laid. Okay, so as the number of chickens increases, the number of eggs increases. More eggs means more chickens hatch. So as eggs increases, chickens increases. Therefore, we have a reinforcing loop. Okay, the chicken and egg reinforcing loop. It's not a particularly exciting one, but it is a reinforcing loop nonetheless, where we've got, in this case, zero minus signs on our polarity. So you get more chickens who are laying more eggs, who are hatching into more chickens who are hatching more eggs, and suddenly we've got world domination by chicken in our reinforcing loop. Okay, with that in mind, with that scary thought, and don't worry, we're going to do something about the total world domination of chickens a little bit later. But for now, I'm going to put you into your groups, and you're going to have a go at building a causal loop diagram. And the diagram that I want you to build, I want you to describe the causal influences that are influencing people adhering to social distancing and other preventative measures during the COVID-19 pandemic. So obviously, I'm going to see what you, a bit of creativity, see what you come up with, but just get you used to using and drawing up these diagrams. So what you should do, start in the center of your page, or however you're going to be doing this, and write a series of entries that might cover different measures. So things like, number of people wearing masks in required settings, or number of people staying 2 meters away from individuals not in their household, or number of people washing their hands regularly, that kind of stuff. Then once you've done that, once you've thought of a few there, start thinking about as many factors as you can that will directly influence each of these numbers, okay? And which are directly influenced by the numbers of people adhering to these measures. So what are the things that will influence those things that you've written? And what are the things that these things will influence? And for each influence that you write down, you should note either note the polarity, so put either a plus or a minus to indicate whether they're both going in the same direction, so one goes up, the other goes up, or in opposite directions, so one goes up, the other goes down. And you should put your polarity at the end of the arrow, so wherever it's pointing. Once you've done that, then start to build it out. So then if I've written in a factor here that influences this, then I can think, well, are there factors that then influence this in turn, and gradually build it out. And every time start building out, and also looking at everything you've written down to say, well, does that influence something I've written over here as well? So start gradually building it up, all the factors that you think that might be starting to interlink and what they directly influence, etc., etc. And just gradually keep building it up. But as you're building it up, constantly be on the lookout for any potential loops. Are there loops that are emerging? And if there are loops emerging, are they reinforcing loops or balancing loops? And if you see a loop, what's that telling you? What insight can you generate from that? Okay, so I'm going to give you, so it's 2 o'clock, so we'll resume at quarter three. So take about 40 minutes and then take a 5-minute break before we resume, and have a go at this in your groups. Just gradually build it up, and I'll get a couple of the groups to just present their maps when we come back. So just have a think about what are the kind of influences, and get used to putting together these diagrams. Okay, let me stop sharing and I'll open up the groups. Hi everyone. Okay, welcome back. Managed to bounce around most of you, I think, to have a look at what you're doing. So some nice little maps that I saw. I wasn't expecting anyone, by the way, to have solved the COVID crisis by drawing a causal loop diagram in 40 minutes, but this was just to get you a bit of practice on what these causal loop diagrams look like and how you can build them up. And as a number of you, I think, discovered, they get quite messy quite quickly, and that's a common thing, particularly when you're not using specialist packages. But obviously I'm going to show you Insight Maker shortly, which is a better way of doing this. But just before we go on, I'm just going to pick on a couple of the groups just to share what they've been doing. So I will bring up the trusty wheel of names, and we'll see who's first up. And I think it's going to be, Marvin. So someone from Marvin, do you want to just talk us through your map and any insights you may have had?
Yeah, I can I'll get it. Despite using Insight Maker, it still turned into a mess. I don't think we're using it properly, but we tried.
Yeah, no worries.
But yeah, as I say, kind of a bit of a mess, but we kind of first started with a number of people infected with COVID and what effect that would have. Obviously, it would increase public awareness, and that would increase people wearing masks. But then we had this thing where the more people wearing masks would lead to the level of COVID going down, and then that would change perhaps people adhering to other measures, such as like the 2-meter rule, or kind of traveling. And we also had the number of people with steam glasses going up as more people were wearing masks, and how that might feed into the fed up attitude of people towards measures. So yeah, just lots of bits going on, but as you can see, a bit of a mess.
Yeah, that's good. I like that sort of central balancing loop that you picked out there. I mean, that's in some ways it kind of makes sense, doesn't it? I mean, that's what we're essentially all going through, a giant balancing loop where, as in any pandemic really, that your, case numbers go up, so restrictions increase to bring them down, which you would hope that's what they would do. That's the purpose of them. And then that, as that brings things down, then restrictions start to ease, and then cases go up, and then it's that sort of balancing loop that we're all kind of living in. But you're quite right. Really good point about how that can, a lot of this can spill out to other things. And so you could argue that that kind of balancing loop is causing issues elsewhere, because people getting fed up of particular measures that they're starting to see, starting to get aggravated with it, and that could then affect compliance of people doing this kind of stuff. So some interesting dynamics at play there, I think. Brilliant, fantastic, thank you. Right, let's just pick one more group. Share my screen, spin it again. It's going to be one of the blue ones. It's going to be Max, I think. Yep, somebody from Max.
Hello. Seasonal. In the shape of an elf's boot or something. We had similar discussions as the other group, really. Lots of sort of quite small inner loops that were sort of self-balancing. We also tried to work in eggs and chickens over here as well. So
I like that.
yeah. So increasing numbers would increase the number of lockdown hen farms, and then chickens and eggs take care of themselves from there. But also chickens would then increase the number of people washing their hands regularly. And so we just kind of went around these loops. I've got reading the Daily Mail. So for example, social distancing, so that increases and you feel more sort of affinity towards your fellow man, and sense of solidarity. You might read the Daily Mail less, and so forth and so on. Yeah, so just had to play around with it, really.
No, that's great. Yeah, I love the I love the fact that your model could partly be used to try and argue that we should have a chicken takeover, because that will help hygiene measures.
Yeah, it's the hidden epidemic, isn't it?
Yes, absolutely. Yeah. So we are right to focus on chickens, which is an excellent segue into what we're going to do next to tackle the chicken issue. Although clearly, I think we need more chickens, and maybe maybe we shouldn't do this next exercise. Fantastic. No, it's great, and hopefully it's given you all a bit of practice on how to do this stuff. Okay, let me share my screen, and we'll move on to the next bit. Right. Where are my slides? Here they are. Oh, no. Again. There we go. Fantastic. Okay. So we've talked about qualitative system dynamics. So that's basically where we're not really plugging in any numbers. We're just building these causal loop diagrams to get a bit of an understanding about what things influence other things, and the directionality of those influences in terms of the the polarity, whether the things are moving in the same direction or in opposite directions. And as those things link together, are they forming loops? And is that are those loops balancing themselves out, or are they reinforcing? You getting either a negative effect that's constantly snowballing, or maybe a positive effect that's snowballing, something you want to encourage. But now we're going to talk about basically plugging numbers into this stuff. So let's go back to think about our chicken and egg system, our nice complex system over here, where we said we've got chickens, and there's more chickens. Chickens lay eggs. More chickens means more eggs laid, and more eggs laid means more chickens. Now, what we can do here is we can build a quantitative system dynamics model of this system, because we can attach numbers to this that will describe the rate of flow between elements in the system. That is the rate of flow between chickens and eggs, and the rate of flow between eggs and chickens. In other words, how many eggs chickens lay per unit of time, and how many eggs will hatch into chickens per unit of time. So before we go and do that, we're first going to need to understand some of the core principles of system dynamics models. So there are various building blocks whenever you're putting together a system dynamics model. but the key ones that you will always be using are these four here. And so these are the basics we're going to cover today. So you may have come across system dynamics models before. You may have heard them referred to as stock flow diagrams. That's basically a system dynamics model. And so a good way to think about system dynamics is kind of like a plumbing system. Okay, and this will make more sense as we think about it. So let's start with this idea of stock. So in a system dynamics model, we've got these things called stocks, and a stock holds the stuff that is flowing around the system. So imagine like a tank of water. Okay, so your stocks will hold, you've got something flowing around your system, and your stocks will hold that. The way in which they flow around the system, though, is using these things called flows. So flows allow your stuff, whatever your stuff represents, to move around your system. And the rate at which the stuff flows can be controlled by like a valve. So again, imagine water flowing through pipes. So you can have things flowing between these stocks, a bit like water flowing between tanks, and you can control the rate of that flow. We also have these things called variables. So a variable in system dynamics is something that's not otherwise captured by the model. In other words, it's not a stock or a flow, but it will be something that will influence a stocks level or a rate of flow. Okay, so if there's something else we want to describe, so well, that will actually influence the rate at which things flow from this to this, or that will influence the level of this stock, then we can include it as a variable. And if we do that, we can use these things called links. And links are basically, we use those to link up variables and stock levels to say that a stocks level or a flows rate is affected by a variable or by another stocks level. So we could say this flow rate here, the laying of eggs, that's influenced by the laying rate here. Okay, so we could set up a variable, and the thing that would link this variable to this flow would be this, a link. So there's nothing unlike it. So flows and links are similar, but flows are actually moving the stuff around, and links are just saying this thing can influence this thing, but there's nothing flowing between those things. Okay, so you've basically got stuff sloshing around your model. It accumulates in these things called stocks. It flows along your pipes, which you call flows, and the rates at which those things, that stuff flows around, can be also influenced as well as by stock levels, but also by variables. And you can create links that will indicate that a variable will influence a flow rate, for example. This will make more sense when you come to see it. So let's go back to our chicken and egg model. Let's say that we know that, for example, chickens lay on average 5 eggs per week. And we know that fertilized eggs take on average 21 days to hatch. Okay, so what we'll do in our model, we'll start with 100 chickens and no eggs. So we're gonna start with the chicken. The chicken came first in our model. So we've got 100 chickens at the start, no eggs. And let's say we want to track our chicken and egg populations over time. So we basically want to use a model to try and work out what we think is going to happen in our system. So chickens, 5 eggs per week that they're laying, and fertilized eggs taking on average 21 days to hatch. Now, before we go on, there are some quirks of system dynamics models that are a little bit different to the way in which you're used to modeling using the other approaches we've taught you. And it's worth knowing this stuff right from the start, because it can seem a bit unusual at first, but you have to kind of think of a flow, a mass of stuff, a continuous mass of stuff like water that's flowing around your system. And that's why it's a little bit different in terms of how you represent things. So that's the first thing to bear in mind. Your entities is not like discrete event simulation where you've got individual entities coming into your system, they're queuing, and it's not like agent-based simulation, certainly, where you've literally got individual agents and they can all act differently. But the stuff, whatever you're representing is your thing that's flowing through your system, is just represented as a continuous mass. Okay, so it's like a liquid. Another thing to point out is that system dynamics models are not, by their nature, stochastic. Instead, they're deterministic. That means every time you run a system dynamics model, you'll get exactly the same results. Now, there are ways in which you can make system dynamics models stochastic, and you can include things like distributions, but strictly speaking, pure system dynamics is deterministic, because it's not actually, it's not the individual entities that are coming into your system you're worried about. You're looking at the overall dynamics of the system. What about the way in which this system is configured leads to these kind of dynamics emerging. So in that way, they're actually deterministic by nature, because every time you run them, you should get the same result. And another thing to say with system dynamics models is we're generally interested in kind of the general patterns or dynamics within the system, rather than trying to make predictions such as, you need so many doctors to meet that demand such and such % of the time, like you would with a discrete event simulation. It's not so much about that. You're trying to look for structural patterns, structural dynamic patterns that are emerging as a result of the way in which your system is configured. And that's the key difference with system dynamics, really. So let's take a look at one of those quirks now for the chicken and egg model. So we said the eggs will take on average 21 days to hatch. So let's imagine we have our time unit in our model, and it represents weeks. Okay, so we know that chickens lay on an average of 5 eggs per week. So every tick of the model, every time unit that elapses will represent 1 week. So how do you think we're going to describe the number of eggs hatching per week?
.3.
You're on the right lines. You're on the right lines.
A third of an egg a week.
Yes, it's in fact eggs divided by 3. Now, if you're sitting there thinking, what on earth are you talking about? Let's think this through. So the way in which, so we know that we got our chickens laying on average 5 eggs per week, and we know that, and our time unit is going to be a week, and we know that it takes on average 21 days for an egg to hatch. So basically what that means is that every time unit, every week, the number of eggs that will hatch will be the number of eggs divided by 3. So if we think about that, if we had 1 egg, it would take 3 weeks, 21 days to hatch. Now, in system dynamics world, unlike other modeling methods where it would, assuming you were using a modeling method to model an egg, but if you're using, discrete event simulation or agent-based simulation, for example, then you'd say, well, you wait 3 weeks and then the egg hatches. But that's not how it works in system dynamics. In system dynamics, that means if an egg takes 3 weeks to hatch, that a third of that egg would hatch per week. Okay, even though that's impossible. But that's how it works. Okay, and again, it goes back to this idea: you've got sloshing stuff flowing around your system. It's a liquid. It's a continuous mass. So not mash, a mass. So a third of an egg hatching per week is entirely reasonable in system dynamics world. So if we had 2 eggs, obviously each week 1/3 of each egg would hatch, which means after week 1 we'd have 2 1/3 of eggs hatched, or 2/3 of an egg. Because if you think about it, after 3 weeks, if we had 2 eggs, we'd expect 2 chickens, assuming they're all hatching, as I say. So that would be 3 times 2/3, 6 over 3, that would be 2. So basically we're saying that the number of eggs hatching per week is the number of eggs times a third, which we just simplify to number of eggs divided by 3. Okay. It's a bit weird to get your head around that when you're not used to doing that, and that's the kind of way you need to think if you're going to be using system dynamics models. So the package we're going to be showing you is actually a really nice package called Insight Maker. It's a online model building software primarily for system dynamics. It does do agent-based stuff. I've never used it for that. And I think that I would, if you're doing agent-based stuff, you really need kind of full control of what you're doing, and so something like Mesa will allow you to do that much more easily. Agent-based stuff never works very well when you're using a drag and drop interface, because you always still have to code the behavior. But it is very, very good at system dynamics, and it's basically drag and drop, which means you don't need to have any coding knowledge. Anyone can use it. It's completely free. It's open source. You don't need to install any software. It's all web-based, so you can just log, as long as you've got a free account. You can build your models and you can share them with anybody you want anywhere in the world. So let's have a look at Insight Maker. If you go onto Insight Maker, the first thing you'll see once you log in is this screen. This has got some models I've built in the past, or ones that I've cloned. I'll come back to that in a moment. But for now, I'm just going to create a new insight using this big button here, and I'll just show you some of the features. Now, you may want to read that in your own time. It gives you some of the things, the steps of building a model, and some of the nice things that you can do, including something called stories. Stories is a really nice feature of Insight Maker that allows you to put together a sort of narrative that somebody can watch the model being built up, and you can explain things. It's actually a really nice thing to do. I'm not going to go into that today, so I'm just going to click to clear that demo model. So all your building blocks basically are here under this add primitive drop-down menu. So if I click on that, it's got the various things that I can add. Now, the stuff around agent base, you can ignore that. The stuff around user interface, you can put in text fields and buttons and stuff like that. I'm not going to go into that today, but again, that's something you might want to check out yourself. But the main things are going to be up here, particularly stocks and variables that you'll need here, and flows and links up here. So let's imagine that we've just got a simple model where we've got one thing flowing into another thing. So if I want to add a stock, I just click on stock and it'll put stock there. I can drag it wherever I like. If I double click on it, I can rename it. So I'll call mine stock A very imaginatively, and I'll push enter. And let's imagine that I want stuff from stock A to flow into stock B. So I can click add primitive, add stock, drag that wherever I like. It's got that nice little red line that comes up when you're lined up. And then I'll just call that stock B. And then if I want to have things flowing from stock A to stock B, then all I need to do, so up here, you can switch between whether you want to draw flows or links. And remember, flows are the kind of pipelines for your model that stuff will actually flow from one stock to another. But links are just saying this thing, usually a variable, will influence this thing over here. In other words, I want to use that number over there, but nothing's going to flow from one place to another with a link. So let's imagine I want to flow. That's selected by default, but you can click on it to make sure. And if I hover over the starting stock, you'll see a little arrow appear. If you left click on that and then just drag it to the stock you want and let go, and it sets up a flow. So I've now got a model where I've got a stock A flowing into stock B. Okay. Now let's say I also want to well, actually, let me just start by clicking on some of these elements here. So if I click on stock A here, you'll see various things. Let me shift that. Various things will appear over here on the right, and depending on what you click on, whether it's a stock or a flow or a variable, different things will appear over here, and you can change various aspects of your various components. So you can change the name, or you can just double click to do that. You can put in little notes. This one's usually quite important on a stock. So I always find this a bit odd. So by default in Insight Maker, it will allow you, it says this allows negative set to yes. That basically means you can have negative values in your stock. I think probably for most of the stuff you'll be doing, you won't want that to happen. You might, but just be aware that that's on by default. So if your stock level reaches 0, it'll keep flowing stuff out of the stock, and it'll just go into minus figures. But that's usually not what you want. And I just find it a bit odd that that's the default. You can also set up an initial value. So basically that's how much stuff, whatever your stuff represents, you've got in at the start. So I'm going to change that to no. And then I'm going to put 100 units of stuff, whatever my stuff is in this model. So stock A will start with 100 units, and stock B, which I'll also say can't be negative, will start with nothing. I've also got options there. I can, if I select yes to show value slider, that means, like you saw with the Mesa stuff, that if I put yes, the user who's playing around with this model can use a little slider and they can change the various stock levels or whatever it is that you're configuring. And then you can have various validation methods down here in terms of max and min constraints, but we won't worry about that for the moment. So at the moment, I've got a stock here that's got 100 units of stuff in it and stock B that has nothing. If I click on the flow that goes between them, so by default, the flow rate will be 0, which means at every time unit, 0 units of stuff moves, which obviously means there is no flow by default. But I can change that. So let me just, in fact, let's just set it up initially. So I'm going to have it so that 10 units of stuff move. Oops, 10 units of stuff per time unit will move. So it should take 10 time units to move from 100 units over here to 100 units over here. If I click simulate, let's see what happens. There we go. So it's started up with this graph. And basically one of these lines, oh, I forgot it does this. Sorry, it's when I'm sharing it, it doesn't allow me to resize this. So I'll have to explain it to you. So I'll have to hover over and hope that it comes up okay. When you do it on your screens, it'll be fine. I had this problem last year. So basically one of these is tracking stock A, which is the green line. So remember that started at 100 and then it's tracking that over time. So in the first time step that goes down to 90, the second time step 80, etc. But because it's continuous, you've got this continuous line. So that's gradually going down until it's empty, and then stock B is gradually going up from empty until it reaches 100. And because we've said that you can't have negative values, that stops at 100, and that, if you could see it, would stop at 0. If you didn't turn that on, they would just go on forever. So it would just keep flowing things out of stock A, even though there's nothing left. And so stock B would just get bigger and bigger. Now I've got the challenge of trying to close that window. I may have to refresh. It's really annoying it does that, sorry. Right, let me just put a couple of stocks back in. Try not to resize them. So you can resize them. That was not what I was trying to show, but these little arrows around, you can change the size, you can change the colors and all sorts if you want as well, and then flow from here to here. So one of the things that I might want to do is have more than just having a sort of constant flow rate, is to have the flow rate, which is influenced by a variable. So let me put in a variable here. So if I click on that, you get these little circles, they're variables. So, and remember, variables are things that aren't otherwise included in your model, but which will influence a stock level or a flow rate. So we use links to say that something influences something else in Insight Maker. So if I click link, and then I can do the same principle, I hover over the middle of the thing that I want to start from, and then left click and drag to the thing I want to link to. So in this case, I'm saying this variable can now influence this flow rate. Okay, so if I click on the variable, you can either have just a standard number in there, it might be just a number that you put in, a fixed number, or it might be an equation. And so you can click on this little drop down arrow here, and you can put in all sorts of equations if you wanted to. It's got all sorts of little mathematical functions and all sorts that you can do in there, but it might just be something much more simple. So let's just imagine I've got the number 5 in here for whatever reason as my variable value. So that now links into flow, which means that when I click on the flow, if I were to click on the flow rate as I did before, and then click the left, drop down arrow here. Now, before I just put a number of 10 in here, which means move 10 units of stuff per time unit. But what I could do is I can do something a bit more fancy. And because I've linked this variable to that flow rate, it now means that I can use that variable in whatever equation I come up with. So what I might want to do, for example, is say that the flow rate is double whatever this variable value is, in which case I can just type in this window 2 times, and we use the asterisk for multiplication, as you're used to using in Python, 2 times, and then I can say, I can select with these little green plus icons here. These are the things I can reference because these are the things that are linked to that flow. So by default, you can always link to the stock that it's coming from and the stock it's going to. but that's all you will have by default. But if you link anything else in, like I've done with this variable here, I can then reference that variable. So if I click that, I can then, I've now set up an equation, if I click apply, that says the flow rate here is going to be 2 times whatever this variable is. Okay. Now, in this case, I've just set that to be a fixed value of 5. And so the flow rate will be 10 as it was before. There's nothing particularly exciting there. But this variable may have a more interesting equation. Indeed, this may in turn be influenced by something else, or by another stock level, or by all sorts of things. And so that's when you start to get your sort of interesting dynamics emerge. Okay, so those are the kind of the basic building blocks. You've got your stocks, things flow between your stocks. You can set your initial stock level. Always worth checking that, making sure you don't want negatives, and then changing that, because that's probably going to be the case. You have your flows where stuff is flowing between stocks, and then you have variables which can link up to this stuff. You can also link them to stock levels as well, and the links which link up those things. And you can even have it, so for example, here I could have that the stock level of stock B will influence this variable. So what I could have in here, instead of putting 5, I could say it's half of whatever is in stock B. So then you've kind of got a loop effect there, where the flow rate is in hit between A and B will be determined by this variable, but that in itself is determined by how much is in stock B. Okay, so you can set up whatever dynamics you like in that way. And basically, when you're done, you just click simulate. I won't do it because I have that issue. And you will then get that window appear. Now, actually, I will show you, because I want to show you a couple of other bits. So when you click on this, by default, it'll add in every stock that you've got, and also every variable that you've got in the system. Now, that's not necessarily what you want. In fact, in most cases, it won't be. And there's probably only a few things you're interested in. So what you can do is you can click add display up here. And you can choose the kind of display that you want. So you can have a time series, which is the default, which just basically monitors a stock level over time, or a value over time. And you can choose which data that you want to include. So if you click on that little drop-down list there, I can say, okay, I want to plot stock A against stock B in this, and I can call this particular display whatever I like. And there's various other options you can do there in terms of labeling your axes. You might want to do a scatter plot, same principle. You could do a table, so you can have a table so you can actually see the raw values. And we'll see that in a moment. We'll look at the chicken and egg thing as well. And the agent map, just ignore that, because obviously that's for the agent-based stuff. So you can configure your displays however you like, but just be aware the default is that every time you add something, the default display will come up that it plots everything. So if you've got 20 stocks and 50 variables, it'll plot everything, which I think is pretty useless in most cases. What you probably want to do is compare certain stock levels over time, or you may want to look at variable values over time if they're dynamic, for example, but you probably want them on separate displays. Okay, before I move on, any questions about any of that? Okay, it's fairly straightforward, Insight Maker, and there's lots more to it, and you'll see as you play around with it. There's other things that you can do, which I won't go into here, but it's very easy and very self-explanatory, and the materials are very good for this. But those are the key building blocks that you need. So let's have a look at the chicken and egg model. So here's this model that we came up with before this one here, where we said more chickens means more eggs means more chickens. This is a system dynamics representation of that system. Okay, so here we've got 2 stocks. We've got a stock of chickens and we've got a stock of eggs. Okay, so if I click on the chicken stock, we can see that we start off with 100 chickens, and we can't have negatives. So we can't have negative chickens, which I think is a very good thing. Chickens should always be optimistic. And if I click on eggs, we can see we start with 0 eggs. Remember, that's what I said we wanted to do. We start with 100 chickens and no eggs. Okay. Now, this flow here is fairly straightforward. We've got a flow from eggs into chickens. Okay. That flow represents eggs hatching. So eggs becoming chickens. And in system dynamics world, the egg no longer is an egg. The egg is now a chicken. Okay, which again is a little bit weird. So this is essentially the flow rate of eggs hatching. And if I click on that, you can see that I've put in that equation. So if I go into the equation editor, we said that the number of eggs that will hatch per week is the number of eggs divided by 3. So I've put that in, eggs over 3. So a third of our eggs will essentially hatch per week. However, you might imagine at first glance that you just have a flow going this way from chickens into eggs. Why isn't that the case?
Chickens don't become eggs.
Yes, exactly so. So here, for the purposes of this, we're simplifying to say, well, an egg becomes a chicken. The egg, we are no longer interested in the egg. The egg is now a chicken. But here, where chickens do not become eggs, chickens create eggs. But that chicken remains to lay more eggs, hopefully. So it's not the case that we want to flow from chickens into eggs because things aren't moving out of chickens, but the number of chickens will influence the number of eggs that are being laid. So in fact, what we actually have here is a flow coming into eggs that is from nothingness. Okay, this is stuff coming into the system, a bit like a generator in discrete event simulation. This is stuff entering the system from nothingness. Now, the way, just to flag this up, if you want to do that in Insight Maker, you have to do a little trick. So you have to have, let's say you want this stock here, you want things to flow in from nothingness to it. You have to set up the 2 stocks, then set up the flow between them, and then remove one of the stocks. And that will then create a flow from nothingness into a stock. So just that's how you do it in Insight Maker. So here, essentially, we've got a flow from nothingness into eggs, and that laying of eggs flow is determined by 2 things: the number of chickens that we've got, because more chickens means more eggs, and the laying rate of chickens, i.e. how many eggs do chickens lay per week. So those 2 things together will determine this flow rate. So if I click on the laying of eggs flow, well, in fact, let's click on the laying rate variable first. So I've just specified this as a simple value of 5, because we said that chickens on average lay 5 eggs per week. So the laying rate of a chicken is 5. So the laying of eggs flow, if I click on the equation, is simply the number of chickens times the laying rate. Okay, so each chicken is laying 5 eggs. So if I've got 2 chickens, then the flow rate will be 10 eggs that week. And it's as simple as that. And because I've linked both of those things in, both the chicken stock and the variable here are both linked in using links to this flow, then I can reference them both. When I go into the equation editor, you'll see that they're both linked in here. So I can call them both. So there I click simulate. I won't be able to get out of it, but let's try it anyway. So if I click simulate, now you can see what's happened here. So we've got a table display here, and so I've set it up to be that way. If you're wondering why it's come up as a table, so we can see at time 0, we've got 100 chickens and no eggs. So at the start of the model, we've got 100 chickens, no eggs. That's what we'd expect. Then at time 1, so after 1 week, we've still got 100 chickens, but we've now got 500 eggs. Okay. Then at time 2, so after 2 weeks, we've now got 267 chickens, if we round them up to the nearest chicken, and we've got 833 1/3 eggs. Okay, and we can see that very quickly the number of chickens and eggs starts to explode exponentially. We've got a population explosion of chickens and eggs. So just to explain that a little bit, if just to hammer home this point as well. So at the start, we've got 100 chickens and no eggs. The second week, we've got 100 chickens and then 500 eggs. So if you're then wondering why we've got 266 2/3 of chicken after 2 weeks, that's the 100 chickens from the week before that we already had, plus 500/3 new chickens, because we got 500 eggs in the previous week, and a third of those will now be chickens because they'll have hatched, because a third of those our eggs have hatched. And so they will now become chickens. So we've got essentially 100 old chickens plus 500/3 new chickens, which is why we've got 266.66 chickens. And then here, similar principle, we've got 500 eggs from the previous week plus 500 new eggs. Remember, those 100 chickens will have laid another 5 eggs each, so we'll have 1,000 eggs. But then we've got to subtract the 500/3 that have hatched and become chickens. Okay, so that's why we've got 833 1/3 eggs in the third week. Okay, chickens and eggs. Let's do something with our chicken and egg model. So what you're going to do is you're going to go back into your groups and you're going to expand the chicken and egg model. So the first thing you're going to do is you're going to take a copy of the Insight. Now this is known as cloning on Insight Maker. Let me just refresh that to get out of there. So I've given you the link to the model. There's an option at the top right when you go into that Insight that says Clone Insight. That will allow you to basically take a copy, and you then take a copy of that model that you can play with and you can change to your heart's content. So that's what you're going to do. You're going to clone that Insight, and then you're going to make the following changes to your copy of that model. So so far we've assumed that all of the eggs are fertilizing and they're all hatching. I want you to change that so that not all eggs are fertilized. I want you to make the proportion of eggs that are fertilized a user definable variable with a slider which defaults to 1. Okay, so by default all of the eggs will be fertilized as we've got at the moment, but the user can then change that on a slider to say, you know, only 50% of eggs are fertilized, for example. You should only model fertilized eggs in your model. So anything else you won't include. They never come into being in your model. So you only model the fertilized eggs. I want you to model that chickens can either die through natural causes or predation by foxes. Now, chickens have an average lifespan of around 7 years. Now, foxes give birth to around 5 kits per year. So I want you to start with 100 foxes in the model and no kits. Kits move into adulthood when they start finding their own food at around 12 weeks of age. And foxes have an average lifespan of 4 years. And I want you to make an initial assumption that each fox kills 1 chicken every 5 weeks. And I want you to make that a user definable variable too. So you're basically going to include 2 different ways in which chickens can die. One of those will be simpler than the other, because one of those will require you to include the life cycle of foxes as well. And foxes will eat chickens at a certain rate. So once you've built up that model, I want you to use that new expanded model to answer these questions. Assuming all else is as above, what's the minimum proportion of eggs that need to be fertilized to ensure that our chicken population doesn't die out within 1 year? So keep everything else the same and just vary the proportion of eggs that are fertilized. And then secondly, answer the question, if 80% of the eggs were fertilized, how much more regularly would a fox need to kill a chicken to make the species extinct within a year? Which is quite a murderous question. So apologies, it's quite an odd thing to model, but it's quite good for demonstrating this. So assuming you keep the 80% of eggs fixed that are fertilized, basically how much more regularly do foxes need to kill chickens if they were trying to wipe out chickens? Not that we want to do that for multiple reasons, not least as we've demonstrated earlier, chickens are our way out of this pandemic. But for the purposes of this model, let's imagine where a fox has asked you to build this. They want to get rid of these chickens. How many more are they going to need to kill? How much more regularly to make them extinct within a year? Okay, so I'm going to put you in your groups. I'm going to give you a little bit less now, so we'll come back about 20 past, and I'll ask a couple of groups to share what they've done. Any questions? In which case, I will stop sharing and I'll put you in a group. So have fun. Remember to clone the insight first, otherwise you won't be able to make any changes. And then go to it and see what you can do. Hi everyone. Okay, so I thought I'd bring you back just quickly at the end, just to show you the solution. I was going to get a few of you to show the what you come up with, but in the interest of time, I'm just going to show you the solution. I'll also share the solution with you as well. I think everyone is either there or you're much closer than you think you are, because I think most people are just getting weird behavior, like you've accidentally killed off all your chickens in a week, or you've got too many eggs and they're all it's just something you'll find. It will just be something very, very simple that you've done, so you can cross-check it against the solution. But I'll just quickly share the solution and talk you through it. Oops, no. Okay, so here's the solution. This is on Insight Maker as well, but it's hidden, so I will unhide it, and you'll be able to see in my insights. I'll give you the link to it, but it's the 7B chickens eggs expanded. So the first thing I did here was and a couple of people fell down on this, which is why I sort of gave the clue in there about only modeling fertilized eggs. So we're not interested in eggs that are not fertilized for the purpose of this model. So the best place to put this, the proportion of eggs that are fertilized, is at the start, so that those eggs that are not fertilized essentially never come into being. You could have it that they just, you have eggs and then they become fertilized, but you need to flow them out separately to another place. Otherwise, they'll keep becoming fertilized or have another chance to become fertilized, which isn't what you want. And again, it's one of those quirks of system dynamics that you have to think very carefully about what it's doing, because you can end up tripping yourself up quite quickly. So the simplest way is just to have this laying rate here that was previously just dependent on chickens and the laying rate, is now just, we also multiply it by the proportion of eggs fertilized. So if that's 1, then it'll just run as normal, but if only half of eggs are fertilized, then that will halve the number of eggs that come into being, basically. And that's an easy way to change that. For chicken mortality, what a few of you sort of tripped up on was this idea that you need to ideally separate those things out, because otherwise you'll get into a bit of a tangle. So you don't have to have them going to separate stocks, although I have here just for clarity, but you do need separate flows coming out. So you've got a flow of chickens coming out of chickens who are dying of natural causes, and a flow coming out who are dying through predation. And so you could have them just all both linking into a dead chicken stock, but I've put them separate. So the chicken mortality through natural causes, they'll flow out over here. The rate at which that happens is chickens over 364, because there are 364 weeks in 7 years, and that means that a chicken, 1/364th of a chicken will die per week. So it's chickens multiplied by 1/364, which is the same as chickens over 364. And again, that's just that weird way in which system dynamics works for that kind of stuff. Now, before we come back to that bit, obviously we need to then consider this other bit of the model. So we've got this idea of kits who are turning into foxes who are dying, but also foxes are killing chickens, but not kits. Kits are not killing chickens. So we've got our stock of kits. We start with 0. We start with 100 foxes. The kits are being born. That flow rate coming in that's creating kits is dependent partly on the number of foxes. So much like the eggs coming into being. Because we haven't got foxes turning into kits in the same way we didn't have chickens turning into eggs. So the kits being born is the number of fox. If we have 1 fox, then they will give birth to 5 kits over a year. So per week, they'd give birth to 5/52 of a fox, sorry, of a kit. So then it would just be that multiplied by the number of foxes. Okay, and that will give you the number of kits that are being born per week. And because that flow rate is being influenced by this stock level, we can create this link here between that stock level and that number of kits. Then for kits reaching adulthood, it takes them 12 weeks, which in system dynamics world means 1/12 of a kit becomes an adult every week. So it's kits times 1/12 or kits over 12. Then if we deal with foxes who are dying through natural causes, then that flow rate will be, so they die for 4 years. So it's 208 weeks, which means that that the flow rate would be, again, foxes over 208, because 208th of a fox will die every week. So same principle there. But then we get the interesting bit where they interact, and obviously that's all dependent on foxes. So basically this mortality rate, where you've got chickens dying through predation, is dependent on obviously the number of chickens, but also the number of foxes and the fox predation rate. And so here in fox predation rate, well, it's not really a rate, but we've got a value that we can then pull into this flow rate out here. So if we look at this flow rate, if I go into the equation, so what this is saying is take the fox predation rate and multiply it by the number of foxes. So how many foxes, how many chickens are foxes killing per week? So the fox predation rate is should be number of chickens killed by a fox per week. So here if it's 1, that means every fox is killing 1 chicken per week. So here that flow rate would take the number of foxes. So if you've got 50 foxes and they're each killing 1 chicken per week, then there would be 50 dead chickens per week as a result of predation. Now, what you should have found, if you got all that, and I saw a couple groups managed to do this, you should have found that. Oh no, it's not there. Where is it? The solution. So you'd have found it should be around at least 8% of eggs would need to be fertilized to ensure the chicken population doesn't die out. Anything above that and the chicken population starts taking over, but anything below that and you'll see them die out typically within a year. And you'll find that foxes would need to kill chickens around 5 times more regularly. In other words, 1 chicken per fox per week to make chickens extinct within a year. That rate of each fox killing a chicken per week is what you would need to do if you were the fox and you need to kill off the chickens in a year. So use that to cross-check your model. If you're not quite getting those numbers, that's probably something's gone wrong, but because it's deterministic, so you should get the same results. Have a play around with it and check it against the model solution. So I will link to that. I'll make it public so you can see it, and then I'll link to that so you can have a look at that and check it against your model. Okay, realize we've overrun slightly. Any questions about any of that? No. Good. Okay, fantastic. That's system dynamics. You can kill chickens. That's what it's all about. It's as I say, it's a modeling method to bear in mind, whether you go down the qualitative route, just to help you think about your problems, trying to structure out your problems and focusing on areas of interest, much with network analysis where you're trying to sort of hone in on particular aspects of your system, or whether it is actually the aspects of the system that you're interested in, those dynamics, and you want to explore that. So it's quite a useful little tool for that kind of thing. And hopefully you've seen that Insight Maker is really easy to use. But do check out, if you're interested in system dynamics, do check out the other stuff that Insight Maker can do. It's all really easy to use. It's got some nice little features. But those are the basics, basically, just to give you a sort of basic grounding in the sort of stuff you can do. And one thing Insight Maker does have is really nice visualization, as you've seen. So if you want to show off little models of system dynamic models to people, it's quite a nice one to sort of quickly knock something up and show people how it's working. Great. Okay, we'll close off there. Thanks everyone for coming along, and personal thank you for coming along to all of my training sessions. I hope you enjoyed them. As I say, you will get 3 more of mine when I write them at some point in phase 2. It'll probably be early-ish in phase 2, and I'll share details of that. But otherwise, tomorrow afternoon, there's nothing tomorrow morning. Tomorrow afternoon, you do have the session with Luca, where we'll be going through the ED model in R. And then on Thursday, you've got Sean all day, who will be showing you network analysis, and nothing to do with chickens and foxes this time, I believe. Okay, great. See you again, and don't forget your project pitches, which are due in by the end of Monday. I look forward to seeing what you come up with, and see you again soon. Bye bye, everyone.